All right, let's try something a little different for this next lesson. This is 3.5. We're going to find the zeros of polynomial functions, and that means we're going to start cranking up the powers. Everything we've done lately has been a quadratic equation or a squared equation, and we're going to now see things like fifth power equations right here, fourth powers over here, and I'll take you through a tour. Then we're going to look at just the graphs and try to figure out how many zeros they have, and then we'll look at just an equation, and this one happens to be a fourth power too. And so I'm going to do 5 problems today, and what I'm doing differently is I actually just did a sample of your homework. I picked some problems that are like the homework problems, maybe even the exact homework problems, and put them all on one page, and we'll just kind of go through them one at a time. The reason I'm doing it this way is we're looking at a lot of graphs today, and I wanted you guys to see pretty graphs instead of me trying to hand draw a bunch of graphs. So I had to pull in some sort of professionally printed out thing. All right, so we're going to find the zero. Let's just get to a problem here. We're going to look at the first one, and we can see that it is a fifth power. This is something that really you guys have never seen in your life. Algebra 1, 2, this is not review in any way. This is new stuff. We got a fifth power, and one thing I have been telling you guys over and over is that the highest power of a function is the number of zeros that function will have, or the number of roots that it'll have. There's some different words that almost all mean they mean the same thing, but yet they're slightly different. So for example, when we say zeros, we're saying what numbers could we plug in for x into this function that would spit out a y value of 0. In other words, what can we put into here that'll make that equal 0? That's what zeros are. Okay. Roots. Pretty much the same thing. In fact, for now, let's just call those exactly the same thing. And another word that pretty much means the same thing is x-intercept. And that's more, it's the same thing, but it's more focused on the graph. You're actually saying, where does this graph cross the x-axis? Here's the x-axis over here, and here are the places where that graph is crossing the x-axis. And you'll notice fifth power equation, 1, 2, 3, 4, 5 places. But that's also when something crosses the x-axis, that's also when y equals 0. For example, that point right there might be say negative 1.5 comma 0. In other words, the y value is at 0. Whenever a point is on an x-axis like these are, the y value is 0. Therefore, those x-intercepts are also zeros. X-intercept, root, 0, they all pretty much mean the same thing. All right, so we haven't really answered a question yet. Let's answer a question. This one says, state the possible number of real and or imaginary zeros for each function. Just state the number. And in this case, it's a fifth power equation. We can see that there are 5 places where it crosses the x-axis, so that basically the answer to this problem is 5. Let's go a little faster on the next one. Go over to number 2 here. Once again, we have a fourth power this time. Same idea though, same situation. And we can even see it's a real straightforward problem. It crosses at 1, 2, 3, 4 places, and therefore it has 4 zeros. And that was all they're asking on those first couple problems. How many zeros does it have? All right, zoom out. Let's get into here now. So now we have no equation. It just says find all zeros, approximate where necessary. So here's number 3. And in this case, we don't know what the equation is. I'll tell you what though, I know it has one actual real zero right here. That does not mean this is a first power equation, though. In fact, you can see just by the curve, this thing's going up and down and curvy and all this. There's no way this is a linear first power equation. It's just that the other zeros, and we'll get into this more later, are imaginary zeros, or i's. When you try to solve to figure out where they cross the x-axis, they come out with i's, and therefore they don't actually cross the x-axis. We can't graph imaginary numbers. So since, all we can go by is this graph. It says find all zeros, and so looks like there's only one, and it's at 0. So the zeros is 0. Let's scoot over here. Now this one, when you look at it, looks like a squared equation. It looks like a parabola, which would be a quadratic or squared equation. It could be something else, but all we know that it crosses the x-axis here and here. And so it has, from our eyeballs, we can just see that it has 2 zeros. Those are at -6 and +3. And finally, let's look at something a little different here. This one's where all the work comes in. Trying to figure out how much space I'm going to have here. Alright, finally, here's a pretty messy one. You're going to want to take your time watching this part of the video. I'm going to try to go as slow as I can. We actually have to do some work here. This one says find the zeros. There's no graph. You're not just looking at a graph and looking for where it crosses the x-axis. We actually have to do some algebra and solve this, setting it equal to 0. So step 1 is we're going to find the zeros. So just like any other problem, we are going to take 3x to the 4th plus 2x squared minus 8, and we're going to set it equal to 0. So that's how we'll find the zeros of this, or where it crosses the x-axis. This is going to actually be a factoring problem. The way these ones are set up, it says using any algebraic method, we are going to be able to factor this problem. So the first thing, I think sometimes it just helps for me to get it started, and you'll see where this is headed. But the pattern here is instead of it's x to the 4th x squared then a number. Instead of our typical problem would have been x squared x then a number. So when you see x to the 4th then x squared then a number, we need to realize that that is still going to be able to factor, still going to be in this format right here, but we're going to put 3x squared here and x squared. So instead of, once again, if this said 3x squared here, then we would have put 3x and x. But since it says 3x to the 4th, we need x squared. So the first thing you need to convince yourself is that 3x squared times x squared equals 3x to the 4th. So we have that. And then over here, these two numbers, just like all our other factoring problems, we're just trying to make -8. So, when I think of numbers that multiply to make 8, I think first thing that comes to my mind is 4 and 2. And let's see, I'm just going to be right on this one the first time. I'll put a 2 here and a 4 here. So that does make 8. We have the 8 we're looking for. And notice that the outsides, 6x squared, 4x squared, and the insides can make 2. You got 6 and 4. Well, 6 and 4 are 2 away from each other. So we need +2. So that means we need +6 and -4. Check that out. Let's start over. This is 3x to the 4th. We have that. This is +6x squared minus 4x squared, which is +2x squared. And then we have negative 8 right here. Negative 4 times positive 2, negative 8. But we are far from done with this problem. That's just the factoring part. Now we have to set these equal to 0. 3x squared minus 4 equals 0. X squared plus 2 equals 0. And now we have to deal with each of those. This one here, we're just going to go 3x squared equals 4. Then we're going to divide by 3. And then we're going to take the square root. If we square root both sides of this, we get x equals plus or minus square root 4 over 3. Not a terrible answer. We're going to come back. We'll clean that up here in a second. Let's go to the other one, though. We have x squared equals negative 2. And then when we take the square root of this one, we end up with x equals plus or minus square root negative 2. Which obviously is not normal, and then you get imaginary numbers here. But pretty easy. All we're going to do on that is we're going to put plus or minus I, that doesn't look nice, I square root 2. Whenever we have a negative inside a square root, all we got to do is to take it out of there is just call it I on the outside. We're still in trouble here. These are not real answers. We're not going to see them show up on any kind of graph or anything, but they are zeros. They do, if you were to, we're not going to do it, but if you were to plug I root 2 and plug it in for x up here and do all the math involving i's and all that, it would all cancel out. You'd end up right here. This would be 0. Okay, but as far as an x-intercept on a graph, these do not give you x-intercepts on the graph. All right, back to the other one. What we have, the only reason this is no good, I mean it's good, but we got to finish it, is first of all the square root of 4 is 2. So the numerator is actually just a 2, and the denominator is square root of 3. Remember, whenever you square root a fraction, it's the square root of the numerator, which is 2, divided by the square root of the denominator, which is still square root of 3. And we can't have a square root in the denominator, so our next thing we need to do is multiply top and bottom by square root of 3. So we're multiplying here. And we end up with equals plus or minus 2 square root of 3 over 3. Because square root of 3 times the square root of 3 is 3. That's why we're doing this. We're trying to cancel those out. Or in other words, that's the square root of 9. And the square root of 9 is 3. All right, now there's some answers. There's some answers. Notice that this is a fourth power equation. Look up here at the top. Fourth power equation. And we have 1, 2, 3, 4 answers. Some of them real. These are real answers. They're still not pretty, but they're real. They're not imaginary numbers. They're just decimals that you'd have to figure out where they are on the graph. And these are imaginary solutions. All right, so that's 5 examples. I think that should be enough to get you started in class on the homework. So hopefully you took some good notes. You can bring them to class tomorrow, and we will go from there. See you soon.